Hi, my name is Matthew DeMarinis, and this video is designed to help a teacher utilize this lesson that's titled Detecting COVID-19, Should We Just Test Everybody? The intended audience for this lesson might be a student in high school taking AP statistics, or a student in the first or second year of college taking an introductory statistics course. As we proceed through the lesson, we will do the following. We'll learn some definitions. We'll discuss what conditional probability is. We'll use Bayes' theorem. We'll talk about a spreadsheet that will allow us to examine how a few different probabilities interact with each other. And then we'll be able to answer today's key question is, should we just test everybody? Okay, some definitions. Two really important things that you should know about for any test. When I say test, I mean like a test for flu or a test for strep throat or a test for COVID. The two really important probabilities you want to know from your doctor are what's the sensitivity of the test and what's the specificity of the test. So sensitivity over here measures the proportion of actual positives that are correctly identified as such. You could think of this as meaning a person who walks into the doctor's office actually has COVID, and sensitivity is the likelihood that the test will come back as a positive result. Specificity over here measures the proportion of actual negatives that are correctly identified as such. So that would mean someone walks into a doctor's office, maybe they think they have COVID, they have symptoms, and they don't. So they're a healthy person with regard to COVID, they don't have COVID. Specificity measures the probability that they will get a negative result, which is what should happen, right? They should get a negative result because they don't have the condition. All right, so it seems like both of these numbers are numbers that you would like to have close to 100%, right? Sensitivity, the probability that someone tests positive when we know they have COVID should be close to 100. We want it to be accurate, and we want it to detect the condition. And specificity, if someone is healthy, we want the test to say negative to that person, so we correctly identify them as being healthy. Okay, so there are plenty of examples you can find online about COVID-19 test statistics and their specificity and sensitivity. Generally, what we find, if you were to go to CDC's website or the Center for Health Security.org below, you will find that sensitivity numbers tend to vary from as low as 70%, which doesn't sound very good, to numbers in the upper 90% range. For specificity, based on most literature, you'll find percentages as low as 90% and varying up to the high 90s. Sometimes you even have things that claim 100% specificity. So those sound a little bit more promising. We will be doing a calculation during this lesson. So for the purpose of that calculation, we're going to have a sensitivity estimate of 95% and a specificity estimate of 93%. Okay, so let's keep these probabilities in mind. Suppose we went to a doctor's office. We thought we were going to get tested for COVID because we thought maybe we might have it. And the doctor said to us, well, the sensitivity of the test we're using is 95% and the specificity is 93%. So the question is, how should we feel about these probabilities? Should we feel good about these probabilities? And in order for us to answer that, we have to look at something called the conditional probability. And it turns out sensitivity and specificity are both examples of conditional probabilities. So this is the notation that we use in a statistics class. We say probability of A, and you'll see this vertical line, I'm going to highlight it in red, given B. That's how we read that. The probability that event A occurs given we know event B occurs is the probability of event A and B divided by the probability of event B. So that's the definition of a conditional probability. So it's important that you know this notation. So we can take those probabilities I mentioned earlier, these ones here that I'm circling right now in blue, and we can write them using our new notation. So here we have it, right? The probability of a positive test result, given we have someone who definitely has COVID, is 95%. That's your sensitivity number. Okay. Probability of a negative result, given we have a healthy person, 93%. That's the specificity number. And then you have these other two numbers. This is simply the complement of sensitivity, right? These are the people who have COVID-19 but get a negative result. So maybe that's not such a good group to be in. They walk out thinking they're healthy, but in fact, they're not, and they're not getting the treatment they need. If we look down here, This one is someone who does not have COVID-19 but gets a positive result. So 7% of people are going to fall into that group. This is a special name, this last one. This is sometimes called the false positive rate. And you don't want that number to be high. So 7% of patients are going to walk out thinking they have COVID when in fact, oh, I'm sorry, I should say 7% of healthy patients walk out thinking they have COVID. All right, so let's take a look at some conditional probability from a Venn diagram point of view. So if we were to look at this first probability here, the probability of A given B, we know from our definition that's the probability of A and B over the probability of B. So if we look at the picture, the probability of A and B is this region in the middle where both A and B are occurring. And we're going to be dividing that by the probability of B, which is the circle I'm outlining in blue. Right? So you can see, I don't know, maybe this little red piece, it might take up about a fifth or a sixth of that big blue circle in terms of area. But what about this probability? Probability of B given A. Well, that's going to be the probability of A and B, so you're still going to have that red area on top. However, we're going to divide by the probability of A this time because that's what we know happened. That's our condition. And in this case, what you can see is that area A and B takes up a much bigger section of circle A than it does of circle B. And that means you've just learned a very important lesson about conditional probabilities, that these two probabilities are not necessarily going to be the same. So if you change the order in a conditional probability, then the result you get is going to change. And that's going to be really important to understand what we're going to talk about next. So we go to that doctor's office, right? And we ask them for the specificity number and the sensitivity number. The sensitivity is the probability that someone tests positively given we know they have COVID-19. But that's not the probability we really want, is it? What we really want to know is if I go to the doctor's office and I get the test, right? Keep in mind, when I walk into the doctor's office, I don't know if I have COVID or not. I'm going there to find out if I have COVID. Probability I really want is this: the probability that I have COVID given I've tested positively. That's the probability we really want, which we just saw in the picture before is not necessarily the same as the sensitivity of the test. So that's what's really important, and that's what we're working towards here. Okay, we know by definition it's the probability of having COVID and tested positively over the probability of testing positively. So at this point, I introduce you to another number that's going to matter in this case, and it's called the prevalence, the proportion of individuals in a population that have a given disease or characteristic. So you can see what that is right here. Okay, and this turns out to be a very important number for doctors to consider. So here's a fair question. What do we know about prevalence of COVID-19? So it is August 27th, 28th as I'm recording this. And we do have on Long Island and Nassau and Suffolk counties positive test results of COVID-19 under 1% at this point in time. That certainly wasn't true back earlier in the year. So that means that we have a very small percentage of people testing positively for this thing. Now that's not, of the people who are testing positively, some of them may have it, some of them may not. We know that. But there are sophisticated ways to estimate what the prevalence is, and depending on different estimates for different states in the country here, you get a low of 0.3% for the prevalence to a high of 7.9% for the prevalence. And so for our first calculation that we're going to perform today, we're going to assume that the prevalence is about 4%, which is sort of like in the middle of those two. And what I want to start to do now is represent this as a tree diagram and start to calculate this probability. Because remember, the probability we really want is here. The probability that I have COVID given I've tested positively. So here's our tree diagram. We've got a patient from the population. 4% of them have COVID. And there's that sensitivity number that you expect, right? Here's the people who don't have COVID. And here is the specificity number, right? There's the false positive number. Okay, so how do we find the probability we want? We need to know the probability that someone has COVID and tests positively, but those people are here. And we also need to divide that by the total percent of people who are going to test positively, which comes from two groups. It comes from the group I just mentioned, and the other people who test positively are here. So that's how you're going to get your denominator of a conditional probability. So if we do our calculation, here's what we get. Here's the 4% of the population times the 95% of those 4% that are going to test positively, right? That's our sensitivity rate. And on the bottom, here's that same group of people again who tested positively, but we need to add to that, out of the 96% of the population that are healthy, there's still 7% of those that are going to test positively. So you would have to take the students through this calculation, draw the diagram with them, and things like that. And then you're going to get this number. And this is where, as a teacher, you want to take some time and let the students try and figure out what that number really means. That is a pretty interesting number. So that's something we care about. What does that number really tell us about this test? So what it ultimately means is that if you test positively for COVID, there's only a 36% chance that you actually have it. That's pretty amazing, actually, when you think about it. It seems like a very low percentage, given that the sensitivity was 95% and the specificity was 93%. So what's happening here is the question: how could this number be so low? And these questions will lead us towards that. Like, what if we had a higher prevalence? What do you think might happen in this probability? Do you think it would change, and how? What if we had higher sensitivity? What do you think would happen? How would this probability change? And it turns out, to answer all this, so what we really care about is how these three things interact, how this prevalence, effects, and sensitivity and specificity all interact with each other and affect this probability of you really having COVID when you test positively. And so to do that, I've made a spreadsheet that you can use. So here it is. And what we have in here, if we look carefully, we have the sensitivity rate of 95%. And this number, 7%, is the complement of specificity. It's called the false positive rate, right? There was a 93% specificity rate, a 93% of testing negatively when the person doesn't have COVID, which means that when someone doesn't have COVID, the other 7% of people are going to test positively, your false positive rate. And what we've done below here is I've made a spreadsheet for you that has a bunch of different prevalences for you to consider. So here's a familiar one, 0.04, which is 4% of the population prevalence. And there's that 36% that we had before, right? And what you can start to do now is consider what would happen if the prevalence changes. So for example, what if the prevalence was 6% and the specificity and the sensitivity stay the same? Well, then this would be true, right? 46% of you people tested positive would actually have COVID. So what it looks like is when we have low prevalence numbers like 2%, 4%, 6%, then we end up with, oops, sorry about that, we end up with pretty low probabilities, pretty low likelihoods of you actually having COVID when testing positively. As the prevalence increases here, as you see it going up, you'll notice this probability is getting higher and it's getting closer to 1, which is what we would want. Another thing you might want to do is consider, well, what happens if the sensitivity were lower? If you remember in earlier slides, we said the sensitivity could be as low as 0.7 or 70%. So let's change this 95 to 70%, 0.7. And then I would encourage you to look at those probabilities. They all change, and let's go down and take a look at it. Well, at 4%, it looks like we're now down to 29%, right? That is lower than it was before. Here's 6%, it's down to 38%. So what we can see is that the sensitivity gets lower. As it goes lower, our likelihood of actually having COVID when tested positively also goes lower. Let's put that back at 0.95. And the lowest specificity that we had was around 90%, which means you have a false positive rate around 10%. So let's say we do 0.10, right? And we'll hit enter now. And if we go down to 4%, that number, it's dropped all the way to 28. So it might be the case that the false positive rate going up or specificity going down has an even stronger effect on this probability we really want, right? That's pretty wild. You can find a few rogue articles that claim this false positive rate for some COVID tests is up around 30%. That's just not common based on the literature, but let's just take a look at it anyway. Suppose the false positive rate was 30%. Watch these probabilities, and they just drop off dramatically. And if you think about it, maybe that's not so surprising. That's because we have 96% of our population, right, who are healthy, and then 30% of that 96% of the population are being included as people with positive test results. So that brings your denominator up a lot in your conditional probability. What's neat about this spreadsheet also is if you take the time to look through it here, there are some, hold on a minute there, there's a nice chart for you to consider. So you can look at that. Let's just try and lower it a little bit for you without having a little bit of mouse trouble here. Okay, sorry about that. And let's click again. You can see this here. Oop, no, I'm not doing well. Hold on a minute. Okay, there we go. And you can see along the bottom here the prevalences, and then you can see these probabilities. It sort of takes a while. This number, this horizontal line up here is 0.75, right? So with that very high, a very low specificity number of 70% and a high false positive rate of 30%, we get, it takes a long time before we get reasonable results. So this is how you probably end the lesson, is have students write down some sentences that summarize the relationship between prevalence, sensitivity, and specificity. And it should all be stated like as rates. As one goes up, the other goes up. So as sensitivity goes up, then the probability of actually having COVID when testing positive also goes up, and so forth. Those are the kind of sentences you want them to write. I would also say that you could differentiate this lesson and let students who are better with spreadsheets or understand the lesson well try and build the spreadsheet on their own rather than just give them this one to work with. And you could see my formula up here, so the kids can copy that. But you don't want to do that with them. You would rather them try and figure that out on their own. I think you'd be pretty happy. Some kids would probably really enjoy that. Okay, well, I hope you enjoyed this, and thanks for watching.